we are into the final concept of this unit, absolute continuity. Definition is as follows. A real valued function f defined on an interval is said to be absolutely continuous on the interval if for given epsilon positive there exists a delta positive such that the summation of the absolute difference between f of xi prime and f of xi to be less than epsilon for a very finite collection of disjoint intervals, say xi prime, along with the property that the summation of the absolute difference between xi prime and xi is less than delta. So I will come again. A real valued function f is said to be absolutely continuous on that interval if for given epsilon positive there exists a delta positive such that the summation of the absolute difference between those two is less than epsilon for a very finite collection of disjoint intervals, say xi prime, with this property satisfying. So this is a definition of absolute continuity, and one can have a remark that absolutely continuous implies continuity of the functions. So a very absolutely continuous functions are continuous, and have a note that linear combination of absolutely continuous functions are absolutely continuous, but composition of two absolutely continuous functions need not be absolutely continuous functions. So linear combination of absolutely continuous functions are continuous, while composition of absolutely continuous functions may or may not be absolutely continuous. So next, let me move on to some examples regarding absolute continuous functions. So looking into the examples regarding absolutely continuous functions, for the first I will consider a function which is mapped from the interval to R defined by f of x equal to c. So I am considering a constant function for the first. Then given epsilon positive, if I take delta to be equal to 1 or any positive real, then for summation of xi prime minus xi I from 1 to n, which is less than delta, now where this is equal to 1, we have summation of f of xi prime minus f of xi I from 1 to n to be clearly less than epsilon. So clearly we have f of x to be an absolutely continuous function, which is a constant function. Next, if I replace c by x, so f of x equal to x, then for given epsilon, choose delta to be equal to epsilon. So choosing delta to be equal to epsilon, now I have this to be less than delta, which is epsilon. So clearly again this is less than epsilon, so again f of x equal to x is absolutely continuous functions. Next, I will consider another function, say f of x equal to x square. Now given epsilon positive, take delta to be epsilon by 2 this time. Then we have if summation of xi prime minus xi I from 1 to n, which is less than delta to be epsilon by 2, we have summation of f of xi prime minus f of xi I from 1 to n to be equal to summation of, since f of x is defined by x square, this is same as xi dash square minus xi square, and since this is a square minus b square, this is same as summation of xi dash minus xi into xi dash plus xi. Clearly this is less than or equal to summation of 2 times summation of xi dash minus xi. So since this is less than or equal to 2 times summation of xi dash minus xi, and having xi dash minus xi to be less than epsilon by 2, this time we have this to be less than epsilon. So 2 and epsilon by 2, so that is less than epsilon. So again we have f of x equal to x square to be absolutely continuous. For the next, I will consider a function mapped from 0, 1 to r, defined by f to be equal to 1 if x equal to 0, and f to be equal to 0 if x lies between 0 and 1. So clearly this function is not continuous at x equal to 0. So if f is not continuous, there is no need to check whether the function is absolutely continuous or not. So a function which is not continuous is not absolutely continuous. But a function which is continuous need not be absolutely continuous. Having a look at the example, if I have f of x to be x into cos of pi by 2x for x not 0 and 0 if x equal to 0, you can check that clearly f is continuous, but again you check that f is not absolutely continuous. So if f is not continuous, then f is not absolutely continuous, but if f is continuous, then f need not be absolutely continuous. So likewise, I have product and sum of absolutely continuous functions are continuous. So sum of two absolutely continuous functions are continuous and a product of two absolutely continuous functions are continuous. Next, have a quick look at this theorem. An absolutely continuous function is of bounded variation, and the proof is as follows, a simple one. Let f be an absolutely continuous function defined on the interval. Let delta be the delta in the definition of absolute continuity which corresponds to epsilon equal to 1. Then any subdivision of the interval can be split into k sets of intervals, each of total length less than delta, where k is the largest integer less than 1 plus b minus a by delta. Thus, for any subdivision we have t is less than or equal to k. So taking supremum, we have total variation to be less than k, which is finite. So we have f to be of bounded variation. So as a corollary to this theorem, we have if f is absolutely continuous, then f has a derivative almost everywhere. Because if absolutely continuous implies bounded variation, and since bounded variation means then function of bounded variation implies f is differentiable almost everywhere. So an absolutely continuous function has a derivative almost everywhere. Next, heading into an important theorem. If f is absolutely continuous on the interval and f dash of x is 0 almost everywhere, then we have f to be a constant function. So given that f is absolutely continuous and the derivative to be 0 almost everywhere, I need to prove f is constant. So to prove this theorem, I will prove that f of a equal to f of c for every c in interval ab. So in order to prove f is constant, it is enough to prove that if I prove f of a equal to f of c for each c in the interval ab, then it is proved that f is constant. So to prove this, I will construct a function, say e, to be set of all x in the interval, open interval ac, such that f dash of x is 0. So now I am having a set e, so that clearly e is contained in the open interval ac, with measure of e to be the length of the interval, which is nothing but c minus a. Now I will choose two arbitrary positive reals, so say epsilon and neta, to be arbitrary positive numbers. Then for each x in E, if I choose a point in E, for each x in E, there exists a small arbitrary interval x plus h. If I choose a point in x, so for such each x in E, there exists a small arbitrary intervals, say x plus h, which is contained in the closed interval AC. Which is contained in AC. So if I choose a point in x, I can find a small interval x plus h such that it is contained in closed AC, along with mod of f of x plus h minus f of x will be less than neta times h. So I have this condition now. So if this is possible now, by Vitali lemma, by Vitali lemma, now I can find a finite collection of intervals, say xk, yk, finite collection of disjoint intervals which cover the set E, which covers the set E, almost all E, where except the measures, set of measures less than delta, where delta is the positive number corresponding to epsilon in the definition of absolutely continuous of F. So I am having now a set E which is x contained or x in AC such that f dash of x is 0. Now clearly E is contained in AC, and I am choosing two arbitrary positive numbers, and for each x in E I am able to find a small interval x plus h to be contained in AC with the property that f of x plus h minus f of x is less than eta times h. Now if this is the thing, by Vitali lemma I am able to find a finite collection of disjoint intervals xk, yk, which covers almost every set, almost all E except the set of measures less than delta, where delta is the positive number in the definition of absolutely continuous of F corresponding to epsilon. Now if this is the case, I will assume that xk to be less than xk plus 1. So now if I assume that, then I can have a partition of the interval AC to be, if A to be equal to y0, then this is less than or equal to x1, this is less than y1, less than or equal to x2, and so on. Likewise, to be less than yn, which is less than xn, and this is less than or equal to say c, and this is nothing but xn plus 1. So I can have this now, and again in the similar fashion, if I consider the summation of xk plus 1 minus yk, that will be less than delta, and by the absolute continuity of F, I can have summation of k from 1 to n mod of f of yk minus f of xk to be less than epsilon. So this is what I have now. So epsilon times neta, this is less than or equal to epsilon times summation of k from 1 to n mod of yk minus xk, which is clearly less than epsilon times c minus a, and this is nothing but c minus a. Now by the definition of absolute continuity of F, I have summation k from 1 to n f of xk plus 1 minus f of yk to be less than epsilon. So as I took epsilon here, I can replace by the arbitrary neta here now, just to defer that. So I have, by absolute continuity of f, I have this now. Now if you consider mod of f of c minus f of a, this is same as the summation of f of yk minus f of xk with the summation of f of xk plus 1 minus f of yk, which is clearly less than epsilon times epsilon plus neta times c minus a. So now if I consider the mod of f of c minus f of a, this is nothing but the summation of f of xk plus 1 minus f of yk along with f of yk minus f of xk, and this is less than epsilon, and this is less than neta times c minus a. And since epsilon and neta are arbitrary positive reals, I have f of c to be equal to f of a. So which proves that f is constant. So we have next theorem, a function f is an indefinite integral if and only if it is absolutely continuous. So we need to prove that if f is indefinite integral if and only if it is absolutely continuous. For the first, I will assume that f is an indefinite integral and I will arrive at f to be absolutely continuous. To prove that, I will assume that suppose f is an integrable function So if I assume f to be integrable, then I define f to be f from a to b to r by f of x to be the integral of f over ax. So assuming f to be integrable, I will set the function f by integral of f over ax. Now f is absolutely continuous because we have a result that for f to be a non-negative function and f to be integrable over a set say E, then given epsilon positive, there exists a delta positive such that for every subset A of E with measure of A to be less than delta, we have integral of f over A to be epsilon, a well-known result. And along with this, if I consider the summation of the absolute difference of f of xi prime with f of xi I from 1 to n. So this is again same as the summation of mod of integral of f of t over xi prime. And again this is clearly less than or equal to summation integral of mod of f of t over xi prime. And this is equal to, this is nothing but the integral of mod of f of t over union of the intervals xi prime. So this is same as the integral over the union of such intervals. And if you observe that the measure of the union of these such intervals, the measure of the union of these such intervals is less than the summation of length of the intervals. So this is less than the summation of the length of these intervals, and the summation of length of intervals is nothing but the absolute difference of these intervals, and this is less than delta with the help of this result. So clearly xi prime minus xi is less than delta, and integral of f is less than epsilon. So that if f is an indefinite integral, it clearly states that it is absolutely continuous. Now assuming the reverse side, I will assume that suppose f to be absolutely continuous. So assuming f to be absolutely continuous, I need to prove that f is an indefinite integral. Since f is absolutely continuous, f is of bounded variation. We have again a theorem, f absolutely continuous implies f is of bounded variation. So assuming that f is absolutely continuous, I have f to be of bounded variation. Again, by decomposition theorem, a function of bounded variation can be expressed as the difference of two monotonically increasing functions. So I can express f as a difference of two absolutely continuous functions. Now f1 and f2 are two monotonically increasing functions. So having expressed f as two monotonically increasing functions, again since f is of bounded variation, f is differentiable almost everywhere. So that f dash of x exists almost everywhere. In particular, mod of f dash of x is same as f1 dash of x plus f2 dash of x. And if I consider the integral of mod of f dash of x, this is less than or equal to integral of f1 dash of x plus integral of f2 dash of x, and this is less than or equal to f1 of b minus f1 of a plus f2 of b minus f2 of a. So clearly f dash is integrable. So having f dash to be integrable, I will set or construct a function g of x by defining it to be the integral of f dash. So having constructed a function g of x to be integral of f dash, now I will set f of x to be f of x minus g of x. Again, having setting f of x to be f of x minus g of x, since g of x is absolutely continuous and f is absolutely continuous by our assumption, I have f to be also absolutely continuous. So I have f to be absolutely continuous now, and in particular f dash of x equal to f dash of x minus g dash of x equal to 0 almost everywhere. So I have f dash of x to be f dash of x minus g dash of x, which is 0 almost everywhere, and by previous theorem this implies that f is constant. So f dash of x equal to 0 almost everywhere, that implies f is a constant. In particular, I have f of a to be f of a minus g of a, which is equal to f of a. So I have f of x to be equal to f of a now. Since f of x equal to f of a, by our defining the function f of x to be f of x minus g of x, I have f of x to be now f of x plus g of x. F of x is f of x plus g of x, and g of x to be the integral, indefinite integral f dash of x, f dash of t dt. I have g of x plus f of x, where f of x is f of a. So this is f of a. Now I have f of x to be f dash of t plus f of a, which is nothing but an indefinite integral. So assuming that f is absolutely continuous, we have proved that it is an indefinite integral, which proves the if and only if condition for an indefinite integral to be absolutely continuous. Next we have a corollary to the previous theorem. Every absolutely continuous function is the indefinite integral of its derivative. So every absolutely continuous function is nothing but the indefinite integral of its derivative. So it is nothing but if f dash of t is over ax, then it is f of x minus f of a. In particular, if f dash of t is over ab, then it is f of b minus f of a, which justifies for which class of functions the fundamental theorem of calculus holds good, as said before. So this is about corollary, and proof is similar to that of the previous theorem, and the proof is left to you, so prove by yourself. And we are looking into the next definition, which is of singular function. A real valued function f on the interval ab is said to be singular if it has the following properties. We have two properties to obey. F is continuous on AB. The first one is f is continuous on the interval, and the next, there exists a set n of measure 0 such that for every x outside of n, the derivative f dash of x exists and is 0, that is derivative of f vanishes almost everywhere. So I will come again. There exists a set n of measure 0 such that for every x outside of the set n, the derivative exists and it is 0, that is the derivative vanishes almost everywhere. Or combining these two statements, you can simply say that a monotone function on an interval ab is said to be singular if f dash is equal to 0 almost everywhere. So a monotone function which is which derivative is equal to 0 almost everywhere on the interval, so that such a function is called as a singular function. Next we have a kind of problem to solve. We have to show that if a function is monotonically increasing on an interval, then it can be represented as the sum of an absolutely continuous function and a singular function. So I have a monotonically increasing function. I need to express it as the sum of absolutely continuous function and a singular function. So coming to the solution part, first I will consider a function f which is monotonically increasing. So having a function which is monotonically increasing, I will set a function, say g, to be the indefinite integral of f over, say, ax So having g to be an indefinite integral, I have g to be absolutely continuous. So since this is indefinite, g is absolutely continuous, then having this, I will set h to be the difference of f and g. So I have now h to be f of x minus g of x. And clearly, h dash of x is same as f dash of x minus g dash of x. So having h dash of x to be f dash of x minus g dash of x, we have a theorem. If I have f to be an increasing real valued function defined over an interval, then f is differentiable almost everywhere. Along with that, f dash is measurable, and in fact, integral of f over ab is same as f of b minus f of a. So this is less than or equal to f of b minus f of a. So we have a theorem which states that if f is an increasing real valued function on an interval, then we have f to be differentiable almost everywhere, f dash to be measurable, and integral of f dash to be less than or equal to f of b minus f of a. So having f to be differentiable almost everywhere with the fact that f dash is measurable, I have f dash of x to be equal to g dash of x almost everywhere. Since f dash of x equal to g dash of x almost everywhere, I have h dash of x to be 0 almost everywhere, which implies that h is a singular function. You may have a question like this. A Cantor ternary function is continuous and monotonic, and show that, but it is not absolutely continuous. So you may need to prove this, and the proof is left to you. A Cantor ternary function is continuous and monotonic. So Cantor ternary function is both continuous and monotonic, and note that it is not absolutely continuous. And the next note, again this may be a question for you. Show that every absolutely continuous function is uniformly continuous, and what about the converse? Again, the proof is left to you, try to prove by yourself. We have every absolutely continuous function is uniformly continuous, so that an absolutely continuous function is uniformly continuous, but the converse need not be true. That is, a uniformly continuous function need not be absolutely continuous. And as a counter example, again you can take a Cantor function, so that a Cantor function is uniformly continuous on the unit interval 0, 1, but Cantor function is not absolutely continuous. So that this will complete unit 3.